Hey everyone, Morgan here. So we're on the second page of our discussion of the second law of thermodynamics, and it's still a discussion of entropy and where the second law came from. So let's now state it. The second law says the entropy of the universe is constantly increasing. Entropy is always going up, the overall entropy of the universe. Now, can you clean up your bedroom? Yes, that's possible. And in that case, the entropy inside your bedroom has gone down. However, the dirt from your room, the mess, ends up going somewhere else. So the entropy of the somewhere else increases. Let's say that's the trash dump. Okay? So, the total entropy of the universe has gone up, even though the entropy in your bedroom went down. Okay? So we're not talking about an isolated entropy situation. We're talking about the entropy of the universe. Okay? Now, this is a great statement of the second law. This will get you through most of your classes. However, it's not the origin of the second law. One of the first statements actually came from a guy named Clausius, who said, "It is impossible to have a natural process whose sole outcome is the transfer of heat from a colder body to a hotter body." Now, what does this mean? It means if you grab onto a hot skillet on the stove with your hand doesn't get colder and the skillet gets hotter. It's the other way around, okay? The heat goes from the skillet into your hand. It always flows downhill. Now, can you remove heat and make a colder body? Well, it can be done. A refrigerator is a really good example of that. But that's not a violation of the second law, because this is talking about a natural process. And a refrigerator's got a motor that does that work. So we're talking about something that happens without work being done. And when we're in that scenario, heat always flows downhill. Okay? The Kelvin statement came after the Clausius statement. It is impossible to have a natural process whose sole outcome is the transfer of energy as heat perfectly to work. What does that mean? Well, if you're on a steam locomotive and you're shoveling coal into that engine, burning that coal, that releases a lot of heat. But not all of it ends up making the train go forward. A good deal of that heat ends up just coming out and making you sweat, okay? And making the whole area around that engine really, really hot, okay? So, we can't perfectly capture heat and turn it into work. Now, we can capture heat and turn it into work, just not with 100% efficiency. Now, both of these came out of the 1800s. And in the 1960s, a slightly different view about the second law came forward. The Andrews statement, which says the properties of an isolated system eventually quit changing. In other words, they reach equilibrium. Now, the implication of this can be a little frightening. One example, our sun is eventually going to quit burning. Our sun will stop giving off heat, okay, probably turn into a different type of astronomical body. Okay, I don't think it's going to go black hole, okay, but it might turn into one of the dwarfs, and we're not going to be able to live here anymore. It's going to get awfully cold, awfully fast. Okay, it's probably 5 billion years down the road from now. All right, now, is it possible to take all these ideas and put it into a simple equation? Actually, it is. The delta S of your system plus the delta S of the surroundings. That's your total entropy, system and surroundings, okay, will always be greater than delta S of the whole universe, which will always be greater than 0. In other words, entropy will always be going up. in the universe. Happens every time. Okay. That's the second law and all that bit about entropy from the previous page. Now there's some other laws of thermo. The third law. It is acceptable to define the entropy of a perfect crystal to be 0 at absolute 0. Now this is a reference point, okay? We're not saying that the entropy of a perfect crystal is 0. We're saying we can define it that way. On Earth, there are no perfect crystals. We have actually grown them in space. Turns out the biggest problem in crystal growing is gravity. So when you get into microgravity out at something like the International Space Station, you can grow crystals that are practically perfect. Okay? So we can define that low entropy situation to be 0 and then to calculate all our entropies relative to that. Now, for all of this other laws, all of them to be true, there's a prerequisite. That's why it's called the 0th law. It's a prereq. Okay? And the 0th law says if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, A is in thermal equilibrium with B, B is in thermal equilibrium with C, T for thermal, means they're at the same temperature. What do we know? We know that A must be at the same temperature as C. It just has to happen that way. Okay? And if that doesn't hold, then the rest of all this falls apart. Okay? But I think that's pretty obvious. It's just that we needed to state it so that these will be accurate statements for all of the other laws that we're talking about. Okay, and those are the laws of thermodynamics. Thanks for tuning in. This is Morgan, signing off.